Thank you. So I understand that I'm to entertain you until the buses come so that we can go and drink. So I will do my best to do so. And I want to talk about a topic that I've been pushing on lately, which is open infrastructure for an open society. And I'm going to start by giving you a little bit of a vision of what this is all about, and then move towards an actual implementation of walking sort of towards where we want to go with our vision. And so with the vision, I want to start by the notion that we want to ultimately democratize access. And why do we want to democratize access? Because we don't know where the geniuses come from the next round. And so the people who, in my mind, or my favorite formulation of this problem is from The Minds We Need. And you can find this at this, whoops, where's my, there you go. You can find this at this as website. And it boils down to that we want to engage and empower every student and researcher everywhere with the opportunity to join collaborative environments of the future, because we cannot know where the next Edison, Carver, Curie, whatever, pick your favorite genius comes from. And therefore we want to give access to all those wannabe geniuses, no matter where they come from. And so if you then turn this into something that is actionable and speaks to infrastructure, the long-term vision is to create an open national cyber infrastructure that allows the federation of CI at all 4,000 accredited degree-granting higher education institutions, non-profit research institutions, and national laboratories in the United States of America. So where does this number come from? The Minds We Need says that there's something like 3,600 institutions of higher learning that are accredited. I gather another 400 national labs that don't give degrees, and voila, I get a round number with a single-digit precision, 4,000. That's where this came from. And what do I want to do with this? If you think about what are the things that you know of that are open. You know open science, we have an idea what that is. We know open data, okay? We know for sure what open source means, especially among you guys. And what I'm pitching is that in addition to these open entities, we also create an open infrastructure. What I mean by this is that there is compute, storage, data delivery, i.e. content delivery networks, and devices, instruments, IoT, you name it, anything that can provide some kind of compute or data capabilities. And all of those things should be assemblable or assembled or should be able to join an infrastructure that fundamentally can grow horizontally and vertically. So I'm aspiring towards an infrastructure that is open horizontally in the sense that you can add extra devices of all kinds to it, and vertically you can slide capabilities underneath and you can build capabilities on top. And I'll describe to you a prototype of that kind of idea that we're operating right now, where you can indeed certainly add on top and maybe imagine sliding underneath. And I'll tell you how that works and how we build it. Voila, this thing is called the National Research Platform. And if you're aspiring to something this big, you will immediately realize that there's no way in hell that anybody will actually fund it, right? So what you have to create is you have to create a community, and you have to have funded projects that sustain that community. So what we've done is we've found funding to create support the foundations, and then we've created a community that builds on those foundations. And I will describe to you how both of this works in the next little while. And in fact, what we're aspiring to and what we're sort of kind of doing right now is, I'll give up on my pointer. There's lots of funded projects that contribute to this shared vision in different ways. And ultimately, there's the NSF who funded, hopefully for the next 10 years, if all goes well, a foundation that we build a community around it. So how does it work? And let me approach it first from the cyber infrastructure stack. What you see here in the corner down there is the infrastructure stack that we actually operate. So at the bottom you have hardware, then you have firmware, and already at that level we have a mechanism where we can use IPMI from remote in order to run equipment that we don't own but somebody else federates with the system. Then there is another layer on above it. We then, via IPMI, install an operating system. On the operating system, we have that system join a Kubernetes infrastructure. So we have a global we operate right now a global Kubernetes infrastructure that anybody can join anywhere in the world. And then on top of this, we allow for federation of Kubernetes infrastructures. In other words, we have actually done this where we federated between our Kubernetes infrastructure and Google's Kubernetes infrastructure, and we migrate things around in and out of the cloud, and therefore do, via Admiralty, do federation between Kubernetes clusters. We've also done the same thing between NRP Kubernetes and Expanse Kubernetes inside the same data center. So we know that that's possible. And then on top of that, we have some people who run Slurm clusters that get integrated via the standard mechanisms of the Open Science Grid, in other words, Condor, HT Condor. So we have a stack where you can pick your poison at which level you want to integrate, and the bottom line is that the layer you integrate is a choice of your institution. It's your decision because you own the hardware. And ultimately, people make that choice depending on the control they want and the amount of effort they're willing to expend. Think of it, if you want to have zero effort, you give us IPMI access because all you have to do is rack it, connect the network, done. That gives you zero control because we control everything. If, on the other hand, you want maximum control, then you will want to integrate at the OSG level because you run the entire cluster, you run the entire storage system, you run an entire infrastructure in your location, and you join only via an API that joins at the cluster level. And anywhere in between, at every single layer, you could make a choice to federate, join the infrastructure, and you get different levels of control at each layer. That's the idea. Now, this infrastructure that we're currently operating builds on two predecessors. One is the PRP, the Pacific Research Platform. It's a distributed Kubernetes cluster that we ran from 2015 until 2023. Truth be told, basically at some point the money ran out for PRP, and we simply, new money came in called labeled NRP. Voila, we switched the label. The system continued existing, and off we went. So that's really what happened. So it's the same identical Kubernetes cluster, Nautilus as we call it, was just relabeled. The PRP grant during these 8 years started out with 6 states contributing. Now there's 43 states, 19 campuses. Now there's 110 campuses, 9 minority solving institutions. Now 23, you get the drift. We built this over a time of 8 years. And I want to flash by, I'm not expecting you to read any of this. I just want to flash you the institutions that currently use this. So this is the West Coast, the Midwest, and the East. And one thing that is sort of amusing, I've colored them by minority serving institution and by F-score states. And if you sort of look through this, you notice that the West is all green, or a lot of green. It, in a sense, reflects the fact that California have an awful lot of education, or an awful lot of Latinx population. And so a large number of institutions in California, including the majority of the UCs and essentially all of the CSUs, are HSIs, Hispanic serving institutions. And so that's why they get ended up green. Now, the second predecessor that we built on is the Open Science Grid. And this Open Science Grid is really a federation of compute and storage clusters, meaning it developed APIs that allows you to federate clusters rather than individual pieces of hardware. It doesn't federate devices, it federates clusters. And so this right now, this is the map of about a month ago. There's 227 sites registered, and every single one of these dots is either a cluster or a storage system or something like that that is federated with the OSG. The two ways of implementing what I like to call bring your own resource, both of those, the NRP and the OSG, are both open. And in fact, the NRP is actually one of the dots here in this cluster, in this OSG map. In other words, the NRP is accessible via OSG mechanisms from the OSG metascheduler. So you, in essence, have a distributed entity inside a distributed entity. That's how we swing it. And the two approaches for allowing people to bring their own resources are complementary in that one does cluster integration, the other one does device integration. And now let me spend one slide in a moment about who would be so crazy as to give you IPMI access, right? That seems like a pretty crazy idea. And so it's very simple. The people who don't have an interest in deploying operating systems, the people who don't have an interest in operating clusters, the people who don't have an interest in being system administrators, those are the people who give you IPMI. Now, who are those? The under-resourced institutions who don't have the effort but want to play. It's a hell of a lot cheaper to just buy a box with 8 gaming GPUs, and therefore, voila, you can enable all your faculty to be AI researchers or do machine learning training courses, then to build an entire cluster, have the system administration, figure out how to hire sysadmin in an area where there's nobody that they can work with other than you, rural areas in particular. And so those kinds of institutions, and if you look on our map, there's a fair number of them that this applies to. Those are the kind of people. Next, the network providers. Think Internet 2, think Great Plains Network. Those are the kind of people that actually didn't care to operate the operating system. They were happy to place a piece of hardware into their POPs, into the racks in their POPs, and connect with a fiber so that it's on the network. But they didn't want to have all the upper layers of the services that they would have to operate. In fact, even ESNet, when we first engaged in ESNet with this, we operated at the entire stack. Basically, they gave us IPMI access. In order for them to give us IPMI access, they demanded that it has useSD.edu as a DNS resolving entity because they didn't want to get blamed when it gets hacked. Over the years, we've now worked with ESNet for maybe, 4 years, give or take. Over the years, they liked what we did, and now ESNet actually operates its own Kubernetes cluster. So ESNet now effectively allows us to deploy the services layer. So ESNet went from going all the way at the IPMI to now going one up Kubernetes, and we deploy the services into their Kubernetes. In fact, what we really do, we do a GitOps, DevOps. We tell them push the button, and they push the button and auto-install from Git. Now, what's the hardware distribution that we have? This is the locations. This is sort of the NRP equivalent map to this for OSG. And I wanted to, first of all, I want to point out that it's globally distributed. In fact, I cut off Australia. We have one host in Australia that is in Nautilus. And the second thing I want to point out is when you actually go into the US and look at the Midwest all the way to the right here, or the California to the left, you will find a number of unusual locations where you don't expect players that would be playing in this kind of environment. In other words, it actually does work that we integrate a fair number of institutions, CSUs, for example, California State Universities, that would normally never have access to something like this. And so when I had all of those among the greens, all of these California State Universities, not all of them have hardware, all of them have users. Some of them have hardware in the system right now. And I think that's all I had here. Then we originally, this was actually created, this came out of a SAIS award. Most of the hardware originally, most of the compute hardware came from SAIS. And it was funded by SAIS because SAIS wanted to fund a platform that supports the computer science community it funds in order to do AI and ML. And so literally the hardware that is actually deployed, we have about 1,300 GPUs right now. The ML community in SAIS had as alternatives, either they pay the cloud providers, where the cloud providers are restricted to hardware that NVIDIA is allowing them to buy, or they could operate themselves under their desk a system with gaming GPUs, where they pay sort of half the price, less than half the price probably, from what NVIDIA tells them to buy for data centers. So voila, for a while, all of the SAIS-funded folks would buy themselves pieces that they stick under their desks, and that didn't scale. So that's sort of the community we started with. And so an awful lot of GPUs in this system is actually NVIDIA gaming GPUs. One of the ways of looking at the NRP, it's a museum of any and all GPUs NVIDIA has ever built. In fact, it goes back to the K40s. Anything that NVIDIA has built since the K40s, more or less we probably have, including A100s, 80 gig. So it goes all the way to today. We don't have any H100s yet. Then, of course, once you realize this stack, suddenly we realized we actually had created something that allowed the original idea. I used to think of openness only horizontal, because I couldn't imagine how you would build something that was vertically open. However, once you get into the Kubernetes business, you're automatically by default vertically open, because suddenly you're running an infrastructure that actually you can deploy services on top. And suddenly we started out with the machine learners who really were application scientists. And now today we have people, LIGO runs its entire catalog in there. One of our customers, sort of NRP, is the Open Science Data Federation, an entity that's part of OSG in this sort. It deploys a content delivery network into this infrastructure because this infrastructure can operate systems anywhere you want and has an easy way for people to hand it over. And that allows you to have caches in the network backbone. We have caches in the network backbone at this point in 8 different locations we have 20 caches around the world, including caches. We have 3 or 4 or 5 in Europe. We have 2 in Asia. So we're sort of getting to the point where we can actually use this infrastructure to build out services that we never dreamed of providing when we started this. So it sort of becomes a very flexible thing that you can actually build upon. The next step in this is I'm going to send a piece of hardware to Singapore. It will be deployed in the Singaren exchange point. And then we're going to use that piece of hardware. We bought it such that it can simultaneously be functioning as an Open Science Data Federation cache for Asia. And at the same time, it'll be running a replica for the entire PDB, Protein Data Bank. So the Protein Data Bank group is putting the entire infrastructure into containers. At that point, they can deploy it anywhere where there is a Kubernetes infrastructure. Voila, that means anywhere because we have it anywhere. They're going to deploy a replica in Europe, a replica in Asia, and therefore be able to serve those areas of the world much more easily rather than having all of them download data from Rutgers or San Diego. And you could imagine anything else you'd want to run that way. Now, how do we go that when you're building a community, it's really important that you actually can go to this community and say, I got some amount of sustainability, it's worth working with us. And so we had to credibly be able to claim we have 10 years of life. How do you get 10 years of life to fund something that founds the foundation? And that's the next thing I'm talking about. We ended up having about 5+ years via the PRP, and now I think we have funding for another 10 years via NRP. So where does it come from? The NSF has this thing called the Category 2 program. It's a program that is designed to support novel system ideas. The kind of things that have been awarded is there's a Cerebras system that is in Category 2. There's the Habana system at SDSC that's a Category 2. It's those kinds of machines that are Category 2s. And then there's the NRP. And the way that the game is played is that you get the funds for 5 years, and there's an inbuilt renewal as long as you don't screw it up. So you get eventually an opportunity to have 10 years of stable funding to actually build a community around this. And that's what we're trying to do right now. And so this is what NRP now is. Now, and we call this the prototype national research platform because that's the funded piece, whereas we call the national research platform the community piece. So if I get my language straight, anytime I use NRP, I mean the community. Anytime I use PNRP, I mean the actual funded system by the NSF. I almost never get my language straight. But when I wrote this proposal, I asked myself, what's the minimum number of circles to tessellate the continental United States? And so I literally went to Google, copied myself a map, made 500-mile circles, and then I sort of picked. And then I had to put every center in a pop of Internet 2 because I had to put hardware there. And so all the green circles are places where we have caches deployed at an Internet 2 pop. And the 3 blue circles, and you can almost not distinguish green from blue on this. Anyway, there are 3 places where you see it looks like there's some compute and storage deployed. Those are where we actually have GPUs and storage in a data center. One is in San Diego, one in Nebraska Lincoln, and one in Massachusetts. And the idea was that we would establish that we can actually run a nationally distributed infrastructure, and then we can accrete anywhere in the country additional resources. That was the idea. And so we took PRP, made it national, and then built from the funded money data caches such that you had a national content delivery network that everybody could plug into. And in addition, given that this was meant to be a resource that has to be adventurous, we added a number of innovation thrusts. Not only did we do the large-scale distributed, so if you, I'm not expecting you to read all this. Let's just focus on the first 2. 3, 4, and 5 basically turns PRP into NRP I've already talked about. The first 2 is additional thrusts where we have in one location in SDSC, we have an innovative network fabric that allows a rack of hardware to behave like a single node connected via PCIe. This is a technology from Giga.io. Think of it, if you wanted to, at will, create single nodes that have a few FPGAs in it, a few GPUs in, 100 terabyte of NV, or maybe tomorrow 50 terabyte or 200 terabyte. We're trying to create something like that. It's, if I remember correctly, 3 racks worth of stuff. In there are 8 DGXs from NVIDIA. Each DGX has 8 A100 80 gig. In addition, there is 32 FPGAs from Xilinx U55Cs, and then 400 terabyte of NVMe. And you can, in principle, use that, think of it as pieces to then compose a node as I described. Some NVMe, some amount of FPGAs, some number of FPGAs, some number of GPUs, and voila, you do something unusual. And then a second one was we wanted to bring FPGAs to the domain sciences. And the idea was that we pitched to the NSF that at least we ought to be able to do this via some sort of libraries that provide people with a way to do machine learning inference at the very least. And since the proposal got funded, we probably have found enough domain scientists to just keep the FPGAs busy because they all know how to program FPGAs. So our problem has totally shifted. We now have an infrastructure that we're running where some part of the customer community is actually perfectly happy to program FPGAs and therefore want direct access to FPGAs in order to do their science. And so we have, in a funny way, a totally unusual customer community that is very unusual for a standard HPC system that we ended up with. Then I want to talk a little bit about the data infrastructure model. If you want to do something like this, nationally distributed, federating resources, you have a fundamental problem, and that fundamental problem is the speed of light. The speed of light is finite. It doesn't make any sense to have a file system that spans the nation, right? Because at some level, latency kills you. And so we had to make a choice, but at the same time, we wanted to be able to have some kind of federated file system. And so this is what we came up with as a structure. We have the notion of regional self-storage systems, where we think of in a metropolitan area or in a circle of less than 500 miles, we ought to be able to get away with Ceph boxes or boxes of storage being combined into one Ceph system without having completely dismal performance. And we've verified this in PRP, that there's this large fraction of our application and actually can manage 500-mile latencies. So that's one piece of the puzzle. Then when you are going into the wide area network beyond 500 miles, you use a content delivery network so that each and every one of these regional storage can become an origin, a data origin, to an infrastructure that from anywhere you can access via the caches. And so you have a caching infrastructure that delivers access to the data irrespective of where the data actually lives. And that's what we have built, or what we are now operating. Now, the next problem that we have, if you think about, if you want to do something so crazy to combine hardware in 4,000 places, or combine customers, meaning application sciences from 4,000 places, that basically has no limit to how it scales, then you have to somehow figure out, how do you do support? How do you scale out support to a size that you don't actually know how large it will scale? And so we built into the proposal the notion of building a community that can maybe support itself. So Mahidra had to have the pleasure of trying to figure out, how do I support a community that can grow to near infinity? How do I develop the mechanisms to do that? And so in the proposal, we picked people that come from different domains. We picked a number of domains that were targets. And then from these domains, we picked people deliberately who have interests in our 5 innovation thrusts, and picked them such that they had overlapping interests, so that we could build, by design, a community that has enough overlaps that maybe sometimes, or most of the time eventually, they would support each other. And that Mahi and his people that are on budget only have to watch that nobody talks garbage, and sort of basically correct the community rather than totally satisfy the community. And that's sort of the notion that we're trying to establish as a different kind of user support for an HPC system. And we'll see how much there is over the course of the project and how much of this we can actually pull off. Now, let me sort of kind of tell you a little bit of where I would like to go with this. I now have, as PI, an infrastructure with which I can do a hell of a lot of things that I hadn't thought of when I put in the proposal. And so what are the kinds of things that are on my wish list right now? I had put down, before we actually went through the NSF review, in fact, sort of already when we wrote the proposal, I sort of eyeballed, okay, fine, they're giving us 300 plus GPUs. I think we're going to shoot for 1,000 GPUs by 2022. We passed the NSF acceptance review in February, March 2023. At the moment we passed the acceptance review, we had 1,300 GPUs in the system. So admittedly, some are 1080s. So whether that is allowed to be counted, you can argue. But this is what it has. Next is, I want to get to 50 petabyte of storage by end of 2024. I'll show you in a second how that works. But fundamentally, I want to ingest, federate with enough people that bring storage and data that is on their storage to grow the infrastructure's data serving capabilities just by virtue of people bringing the data and the storage that the data sits on, and we just integrate. That's the idea. Then the third one is I want to grow the diversity of the community. I want to do the democratization of science that was sort of the original vision. And we're going to target 2 types of places. We're going to target the CSUs in California. There's 22 of them. That's a bit of a lift. And then we're working where we have on our advisory board somebody from the MSCC, the Manera Surfing, I forget what it resolves to. It's the award that the NSF gave to Internet 2 to serve HBCUs and tribal colleges. And so between those communities, I want to grow customers, basically, application scientists. Now, in addition, I want to introduce new capabilities to the NRP. I want to do machine learning at 100 terabytes. Why 100 terabytes? Well, it's a number with a single digit in front, and that a physicist that work on a log scale, that's a reasonable thing to pick. And what we have inside the SDSC infrastructure, where the 32 FPGAs and the 64 A100 sit, we have 400 terabytes of NVMe. I want to find application scientists who want to use that 400 terabytes of NVMe and train the hell out of using the 64 GPUs or the FPGAs or some combination thereof. Then I want to do domain specific architecture R&D, and I'll talk in a second what this is. I want to do wireless. I want to build underneath. I talked about building on top. I also want to build underneath at the network stack. I want to integrate wireless. I want to reach to the edge into the field. I want to explore the computing continuum. And this is the kind of infrastructure where you can actually do that and do that seamless, I think. Then I want to build fair on top. I'm looking for people who are willing to build on top and provide fair into the 50 petabyte of data that I'm hoping to acquire. So now let me digress a little bit. What do I mean by domain-specific architectures? This is on the left is a plot that I stole from John Schalf from this URL, from this paper. It demonstrates the end of Moore's law. John is convinced that the future beyond exascale is actually in domain-specific architecture. And when he talks about this, and I have not checked this myself, when he talks about it, he says, in your iPhone, there's 7 different chips, each of which does something specific. Meaning the compute power of your iPhone is no longer dominated by a CPU or GPU or anything like this. It's dominated by a collection of different chips. And the claim from both the CTO of AMD as well as the chair of the computer science department of LBNL is that this is where the future lies. I don't know whether that's true, but it is certainly worthwhile seeing whether there's a customer base as domain application scientists that want to explore this. And that's why we picked as co-PI Tajana Rosing, because that's what she does for a living. Tajana is the PI of one of the Jump 2.0 projects funded by the Semiconductor Research, whatever it's called, SRC. She got a $50 million grant to do exactly this. Explore domain-specific architectures designed for ASICs and FPGA. There's multiple others that we have on campus, people that are involved in. There's a total of the 7 Jump 2.0 funded projects. 3 of them have faculty at UCSD that are co-PIs. And that's a customer community. Other customer community is people who do Chameleon. Basically, the kind of people who actually do this sort of thing for a living. We have the right infrastructure for them to play with, I think. And so I'm trying to recruit that kind of application scientists. I mentioned that I'm shooting for 50 petabytes. This is one of the ways that I'm hoping to acquire it. The NSF has the CC Star program. That it stands for Campus Cyber Infrastructure. The CC Star program has between 1 and 2 solicitation deadlines per year. They've been doing this now for 11 years. I think the first came out in 2012. In the last few years, they've added storage as one of the things. And when they offer you a solicitation where you can apply for $500,000 for your campus to build a storage system, they require you that 20% of that storage shall be shared with the community. And there's nobody who you can share it with other than us, because there's no mechanism to share storage with the community in some kind of coherent fashion other than the Open Science Data Federation. And so, voila, they wrote us into the solicitation. And so there is in 23, there are 2 deadlines. One is already passed in spring. The next one is in fall. And this is where I'm hoping that 50 petabyte comes from ultimately, or at least a significant fraction of it. Finally, summary and conclusions. PRP ended and was replaced by NRP. We have a significant new capabilities via the Cat2 systems PNRP. We added lots of GPUs, and we added, of course, all new GPUs. There's A10s in there. We added 3080s, 3090s, A100s. As you can imagine, you cannot go to the NSF and say, I want to add gaming GPUs. That's a no. And so all of the gaming GPUs comes from bring your own resources. Basically, PIs buying them, and then we then running them. And all of them, literally all of the ones that bring us gaming GPUs, they're all machine learners, every single one of them. Then the data volume I talked about the FPGAs. I guess I talked about everything, so I'm done. Thank you very much. Thank you. Questions?
Right here.
So thanks for that very great vision. Maybe I've been working in the cloud for too long, but I see this and I think of a data governance nightmare. Like, no one can really control where their data lives, who can have physical access to it.
Yes.
Can you comment on any assumptions you have with respect to the confidentiality of the data that can flow through NRP?
So there's a whole bunch of things that you just asked that let me unpack. Confidentiality doesn't exist, meaning it's all open. Now that's not quite true. There's actually there's ACLs and so forth. So there's actually we can guarantee that your access is restricted. That we can guarantee. We cannot guarantee that it satisfies any regulatory scheme whatsoever, because this kind of infrastructure cannot satisfy any kind of regulations. So that's why I talk about open, and open means no regulatory requirements for us. So that's one. The other thing that I didn't talk about, but it was on the slides, you asked about how do you give users the ability to have control over where data is located. In my mind, I agree with you, that's a must. It doesn't work that you can say, oh, don't worry a little bit, pretty little head, just access. And magic happens and data is there. I want to give people the guarantees that you at the user level have control when you say, this is my namespace. You as a user should be saying, that part of my namespace should be located only in Nebraska. this part of my namespace should be located only in San Diego, and the middle part of my namespace should be in all 3 locations. And I make that decision because I know that in the middle part I collaborate with people all across, and in the other 2 places I have very specific collaborators. Or whatever other reason you have for doing so. And we wrote in the proposal that we would provide such an interface that people would be able to do this themselves for their namespaces. And behind their back, there would be a lazy guarantee that this would be established over some period of time. And we're building this, where the starting point is, now is Dima around? Because I can never remember what it's called. There is a piece of open source software that Dima mission and found called, I can't remember. It basically allows you out of the box. It's a piece of user space kind of software, if I remember correctly. It allows you to do just that. You can define it out of the namespace that you own where things should be located, and it will just do. So we knew that this exists. Dima uses it for his home use for some time. Does this scale to the scale of our community? We don't know. So part of the experimental part of this infrastructure is to explore how hardened is this software that we downloaded from the internet. Is this viable as a candidate for this kind of solution? And if it's not viable, well, we either make it viable or we'll figure out something else. Does that answer your question?
I have a question. Sarporal, Oak Ridge National Lab. How do you do user authentication and authorization on this system?
It's all done by in common. So we use the fact that pretty much anybody in the academic community, not everybody, but most people are at this point part of in common. And so we authenticate people via their home institution's credentials. So I would authenticate via my Active Directory password at UCSD, just like you authenticate in EduRoam. Exactly like that.
Okay.
I want to thank you very much for sharing this, and please, a warm round of applause for our speaker. Thank you.
Thank you.